Hello everyone. So this is going to be the post-contest discussion for weekly contest 393, all right, of the Leetcode platform. And we have 4 problems in this. So we'll start off with the first problem. First problem reads, you are given a string S representing a 12-hour format time where some of the digits are replaced by the, you can say character question mark, all right. So now it is clearly written that 12-hour formats are in HHMM format, and HH is in the range 00 to 11 and MM is in between 00 to 59. Alright, so the earliest 12-hour period is 00000 and the latest is 11:59. So that makes sense, right? It's basic time stuff. Now, it is written to you that you have the power to replace all the question mark characters in S with a digit such that the time you obtain is a resulting string, and that resulting string which you obtain actually is a valid 12-hour format and is latest possible. Alright, so this is the condition that is given to you. Now, your question is to return that resulting string. Alright, so now by reading this question and by looking at the test cases, you must understand this is a very brute force sort of a question. Alright, you have to just think of a lot of if and else checks, and in the contest also per se, you will then be able to form your answer. So by logic, if we are able to come up with basic stuff, we can actually implement out our question. Alright, so like let's say the input is given 1 question mark, then you have question mark and 4. So forget about this middle stuff. You know that they have given for short that s dot length is 5 and the middle one is a colon. So our concern is only regarding these R, HH and the MM. So according to them, let's say it was given 1 question mark 4. The highest they could have formed is 11:54, right? You cannot change this one, but then you would have been given the power to change this question mark. And it would make sense to make this question mark equal to the highest possible number over here, which could have been 1. You could have also placed 0 over here, right? You could have also placed 0 over here. But if you would have placed 0 over here, the number you would have gotten over here is 10. And you don't want 10, right? Because you know 11 is greater than 10. Do you think you can place 2 over here or 3 over here? No, right? Because you know that the highest R that can denote is 1, 1. So 1, 1 is the max, and since first character is already 1, you cannot keep a 2, 3 or etc. 4 over here. So yeah, that means you only need to keep 0 or 1 over here, and out of the 2, I know I should keep 1. Is that right? Now what about the next question mark? In the next question mark, you can see that since this is empty, and this is the position in the first minute, or you can say out of the 2 MM letters, this is the first M letter which is not present. So if I argue that MM can range from 0 to 59, that means 59's first character 5 over here is the largest you can go. Can you keep this as 6, 7, 8, something else? No. And if you want to keep this as 0, 1, 2, 3, 4, that would be useless because I know 5 is the largest. So if this is empty, I can keep that as 5. That is the largest I can go. So by this argument, they have formed 11:55. And then by reading this test case also, you will get that same idea in your head. Alright, so up till here, I have discussed this example 1 and example 2 is left to you guys, but the problem seems pretty simple now, right? Just by reading the test case, I am building an intuition that the question is pretty brute force, as I explained earlier, and they are trying to maximize something in our head, and we can actually come up with basic if and else checks to see how do we maximize this stuff. Alright, so how do we actually do this? So I'll present those if and else checks and let's see, are we able to confirmate that yes, that is the definite case of creating the maximum HHMM format. Alright, or the latest HHMM format. Alright, so naturally there are going to be 4 cases, right? Naturally it starts with 4 cases. What are the 4 cases? You will say either S0 is given as question mark and you have the power to replace it. Or you will say I have the power to replace S1. Then you will say S2 was also not S2, S3 was also not there, and you will also say S4 was also not there. So you can work on these 4 letters differently, right? Or independently. If either of them are, or you constrain or you put your energy on any one of the letter and you say that is it a question mark or not, then if it's a question mark, you can actually change it according to yourself. And to change it would be a good condition to think in your head. Alright, so we'll start off with S0. We'll try to figure out to go in the S0, S1, S3, S4 manner. Alright, so I'll start off with S0 and I'll say, alright, if S0 was given as a question mark, what do I do? Naturally, if S0 was given as a question mark, what do you think S0 can become in max case? S0, because I know I want to make HH format in S0 and S1, they together combine to make HH, and in this H, the first H, has a maximum value that goes either it becomes 0 or it becomes 1. Is that right? You can either keep a 0 over here or you can keep a 1 over here. Do you think you can keep a 2 over here? No, right? Because this ranges maximum from 0, 0 to 1, 1. That means it is 0, 0, 0, 0, 1, 0, 2, 0, 3, so on till 1, 0 and 1, 1. These are the possible numbers in this. That means the first letters possible characters are 0 and 1. So if S0 is a question mark, you would wish to make it either a 0 or either a 1. Now, preferably you will try to make it a 1 first, right? Because you're trying to make your latest time come first. So, will you argue that let me try and make it 0? I will argue that let me try and first make it 1. So, priority I'll first try to make it the character 1. But now, condition rises is, when do you think I can make this as a character 1? Let's say the character that comes after S0, this character was some character 2 or 3 or 4 or 5. Let's say this was, or so on. Let's say these were the values of S1. Let's say any one value. Let's say S1 was, let's say 3. Then if S1 was 3 and you would have made S0 as 1, then you would have gotten an HH format as 1, 3. Is it possible to create 1, 3? No. That means the value of S0 to be created as 1 is dependent on what is the value of S1. If S1 is the value, either it is a question mark, that means it's not been defined yet, or it's a 0, or it's a 1. In only these 3 cases, you can say that I can make S0 as 1. Meaning, if I write this over here, if I want to make it 1, I know that S1 should be equal to either of these 3 characters, a question mark, a 0 or a 1. If that is the case, then I know I can place S0 as 1, because if I place S0 as 1, then because S1, if S1 would have been 0, good to go, because I would have a format of 1, 0. If 1, then I would have a format of 1, 1. And if a question mark, then I would have had a format of 1 and then a question mark. And then this question mark can be later updated because I am going from top to bottom, or you can say S0 to S1 to S3 to S4 format. So when later I encounter S1, I can change it accordingly. So in either of these 3 conditions, if S1 is either question mark, 0 or 1, I can make it out to be 1. And if it is not any of these 3 characters, then do you think S0 can contain a value of 1? No, because if you make it 1, the other character in the next character that comes after S1, S0, that is S1, will be in 2, 3, 4, so on till 9 format. And you know 1, 2 or 1, 3 or 1, 4, all these are not possible. Are they possible? No. So this becomes my base condition for S0. So I'll make S0 to be 1 only and only if S of 1 is either of these 3 values. Else I'll make S0 to be directly 0. So now I have handled the condition for S0. So S0 is done and dusted. Now I put my focus on S1. Now what if S1 is a question mark? If S1 is a question mark, then what conditions do you have for it to make? Definitely it has a range. You can make it 0 to 9, any character from 0 to 9. Is that right? When do you think you will have to make it 0? Definitely. Or when do you think you will have to make it 1? Definitely. If currently it's a question mark and the previous letter, that is, previous letter is S of 0. Tell me if S of 0 is equal to either a 0 or it is equal to either a 1, because S0 has already been defined, right? S0 has already been defined. No, to be very specific, if only S0 being already defined, if S0 is equal to 1, then do you think if S0 is equal to 1, it would be good for me to make S1 equal to 1 also? Yes, because if S0 is 1 means the first H is 1, and then the second H, which was currently a question mark, if I make it 1 again, I receive the maximum HH value, that is 1, 1. Is that right? And if I see that S0 is not equal to 1, it is any other number besides 1. That is, only possible case, it is a 0. That means else if S0 is equal to 0, that is the only possible other case of S0, then I can make S1 equal to the highest possible character it can contain, which doesn't violate my condition, that is equal to 9. Is that right? Because if S0 is 0, that means first H is fixed, and then the second H letter, which is initially a question mark, can be made the highest possible out of keeping 0 at first. Then, because if you kept 0 at first, that means possible options are 0, 0, 0, 1, so on till 0, 9. Out of these all, do you think it would be optimum for me to go with 0, 9? Yes, because that is going to give me the latest time. So I can keep my second, that is the S1 letter character, as a 9 if I see S0 is equal to 0. So these are the possible two conditions of S1 now. I'm trying to maximize my time. So if S1's dependence is based on S0 and S0 containing only a value of either a 1, either a 0. So if it contains a value 1, I'll say I can make S0 as also a 1, because if the first letter is 1, then 1, 1 is the maximum case, good to go. And if S0 is 0, then best case possible is to keep a 9, that is good to go. So up till here, you must realize that this is not exactly a, you can say, very beginner's problem, and this is a problem that is bound to happen, bound to make mistakes, right? People are bound to make mistakes on problems like this. So this is kind of an ad hoc problem where everything is based on a pattern, everything is based on logic, and you have a lot of if and else checks, right? Definitely, there could have been various different approaches to this, but contest-wise, that would be the first intuition that might come to your head, and that is why my discussion towards it. All right. Now, what about S3? What do you think is going to be for S3? If let's say S3 was a question mark, S3 ranges from 00 to 59. Now, if let's say S3 ranges from 00 to 59, do you think it is any question mark? Is it like, is any boundary or condition stopping you to make S3 equals to 5? No, right? Because if S3 is a question mark, then that means it is open for me to make it either 0, 1, 2, 3, 4, and the last I can go is 5. That is the first M letter. So it becomes from 0 to 59. If you see, I will have first positions ranging from 0 to the character 5. So I can make it the largest character possible, right? Is anything stopping me doing that? No. And same goes for the last letter. So everything above this looks very simple. If I talk about S3, after S3, if I come to S4, if S4 is a question mark, do you think anything is stopping me from making this equal to 9? No, because 9 is the largest character I can go. And irrespective of whatever is kept as S3, let's say it was 0, 1, 2, 3, 4, 5, whatever it is kept at, I can keep 9 in a replacement of that, right? 0, 9, 0, 1, 1, 9, 2, 9, 3, 9, 4, 9, 5, 9. All of the thing is possible. It's valid and it's possible. It's a valid and a possible minute. So if in this I have fixed S3 to be 5, then if I fix S4 to be 9 now, I know that it becomes the largest possible MM, that is 59. So let's say S4 was already defined and S3 was not defined, then you would have made this as 5 and let's say some other letter which was already fixed. So that is also maximum because you have maximized S3. And let's say this was some other letter which was already done, S3, and you had the power to change S4, then you would have placed this as 9. Again, that's the maximum you could have gone. So either way you see that yes, this works and I am good to go. So these are all the ifs and else checks that would be kept on the individual characters. All right, so what I'll do is I'll try to run this on now I'll try to run this on case 2, and then you can actually run this on other cases yourself, and you will realize that this is what happens, and then we can look into the code part. So let's say it was given 0 question mark, then a 5, and then a question mark. So we'll start off this S0. Now S0 is already defined. Can you change this? No. So it remains 0. Right? Now what about S1? S1 is a question mark. You can change it. Now because it's a question mark, you can change it, and the previous letter, that is S0, is defined to be a 0. The maximum you can keep is 9, which we just discussed over here. If S1 is a question mark, keep it 9 if S0 is a 0. So I can keep this as 9 and then a colon. Now this is good to go. I have a 5, cannot hamper this because it's already defined, keep a 5. Now a question mark. Is it stopping me to keep it a 9 over here? No, that's the maximum. I can keep it a 9, and this becomes a valid R. 909 colon 59. All right, so you can actually apply this now again on some of more test cases of your own, and you will realize that yes, this is definitely good to go. This is definitely what is happening in this particular case. All right, let's say I can actually even take a case looking like all question marks. That is going to be much more clear if that's the case. So like, let's say you take the first question mark, you want to manipulate it, you can keep it a 1, right? That's the maximum. Just we said, if it's a question mark, keep it a 1. If I feel S1 is either a question, 0 or 1. So S1 is a question. That means I later have the power to manipulate S1. So I can keep S0 as 1 right now. Now what about S1 now? Now S1 can be kept as 1 because S0 was a 1. So this keeps me as 1. This becomes 5 and this becomes 9. Maximum, yes, 1159 was the maximum I could have gone as a valid R. All right. So if I convert this to code piece, what do you think I'm going to write? I'll keep very simple if and else checks. I'll manipulate the string right and right over here. I'll first see is S0 equals to a question mark. So this is case 1. If S0 is a question mark, then I'll be checking what is the nature of S1. Is the nature of S1 either a 0, either a 1 or a question mark? If any condition is true, I'll make S0 to be 1, else I make S0 to be 0. Pretty simple, right? As I covered over here. Now what about S1? Go on to S1, I'll try to manipulate it. If S1 is a question mark, needs changing. On basis of what? The previous letter. Is S0 equal to 1? If S0 is equal to 1, S1 should become 1. Else S1 will only take the value 9. That could have been the maximum case, as I discussed over here. Now what about S3 and S4? If they are a question mark, no doubt, simply close your eyes, make S3 as 5. And if S4 is a question mark, make S3 as 9. Alright, so this is going to be the correct case in our question. Now what about the time complexity in this? Are you taking any extra space to do any other data structure changes? No. You are doing every change in the string itself. So that means time is constant. And same for space. Space is also constant because nothing is used extra to calculate your answer. And this is going to give you a definite correct answer. Alright, so I think we can now move on to the second problem and see how can we do that out. Alright, so second problem is actually pretty much easier than the first problem, as I felt. Alright, I think you must have felt that too. If yes, you can comment that in the chat box. Because what happens is like, first problem is kind of an ad hoc problem and many of you must have been stuck on figuring out if and else cases in this, right? Even I was. That's not a big deal. But in the second problem, things are much simpler. So let's say I read the second problem. It's given very clearly. You are given an integer array nums and you will return an integer that is the maximum distance between indices of two prime numbers in nums. And it's written not necessarily different. So it's not compulsory that you need different prime numbers, right? They can be same prime numbers also. All right, so now in the nums array, it's pretty clear. You are being given 4, 2, 9, 5, 3. And then you are given this nums, other nums, 4, 8, 2, 8. Now, very clearly tell me, in this nums, they have very clearly said nums 1, nums 3, and nums 4 are prime. So this is 2, this is 5, and this is 3. These are prime, right? 2, 5, and 3 are prime, naturally. Now, it would make sense for me that if I want the maximum distance, do you think this should even be a concern for you, or do you think you need to give second thoughts to this particular argument that if I want to maximize my distance, let's say this is the nums array, this is A1, A2, A3, A4, A5, so on till AN. Let's say I find a prime over here, 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 and let's say here. Let's say I find primes at 4 places. Then because I want to maximize the distance between any two primes, it would make sense greedily that I should take my left end of the prime as this value, and the right end of the prime as this value. This can be my R, this can be my L. Is it any concern now? It makes sense, right? Because you know you want to maximize the distance between any two primes. So if you know that at this position from the leftmost side there was a prime kept, and then from the right position there was again a prime kept, then don't you think you should take this position's index, let's call that index I1, this position's index, let's call that index I2, and then I2 minus I1 is going to be or actually not even putting mod, you can say I2 is definitely greater than I1, so I2 minus I1 is going to be the answer. Don't you think that is the case? And only if you think there is no prime in the given array, then your answer can be -1, because they have given the, I think, alright, no, the -1 case cannot be there, because you can see in the question they have made it much simpler for you now, right? It's clearly given that there is a number, the input is generated in such a format that number of primes in nums is at least once. So you know there is at least one prime number in the given array. So answer always exists. And what can the answer be? The leftmost prime you find and the rightmost prime you find, if their indexes are I2 and I1 or I1 and I2 respectively, I2 minus I1 gives you the answer. Because if out of these 4 primes, possible primes, as an example, let's say in this array which came, it would ideally make sense that this is the largest distance that could have been there between the two primes. Do you think this is the largest distance between the second and fourth prime? No. Do you think this is the largest distance? No. Do you think this? No. Do you think this? No. Do you think this? No. Of course not, right? It would make sense for me to take the largest or the most leftmost and rightmost primes to create the largest distance possible. So now do you think the question is very simple now? But then you will argue, all right, this was something we well understood. But then we saw the constraints and we were not able to figure out that is this feasible or not, if that would have been the case for some people. But then if you actually look at the constraints very clearly, you will understand that this question could have been done like this, as I just explained, in a brute manner. What is the necessity that you are trying to do currently? You are trying to find that first index L from the left hand side, which is a prime, and you're trying to find from the right the first index R, which is also a prime. Is that your concern? So to find the first index L from the left hand side, you would have in a brute manner run a loop in the array with taking such a like an I iterator from 0 to n, or n minus 1 to be specific. And inside this, you would have argued that I need a check to whether C is array of I prime or not. Is this prime or not? Is it equal to prime or not? Or you can say simply, does it passes the prime check or not? If it passes the prime check, then I know L can be made as this I, and I can break right and right over here. Is that right? Very brute solution. First hand which index I found to be a prime nature, I took L as that I value, I index, and broke. So not a big deal anymore for me, right? Now what about this same logic for this particular case, that is finding the rightmost prime? You can do the same thing, right? Same thing, but in a reverse manner. Run your iteration loop from n minus 1 to 0 with an I iterator, and do the same thing inside this as break R to be equals to this I value as soon as you feel that your current array of I crossed or actually fulfilled the prime condition, and break. So this becomes a brute approach. Now in this brute approach, think of the time complexity. Naturally, for finding L, let's say, you are running a for loop, so this runs in O of n complexity. And inside this, you are running a prime check. Now what do you think is the most, like the just basic brute prime check you know? Basic brute prime check simply says, I could have iterated on every value from 1 to array of I, or to be specific, to be more optimum, you can have said I will run an iteration from 2 to array of I minus 1. And if any number in this range is a divisor of array of I, that means array of I is not prime. because condition for prime is it has only two factors, that is 1 and the number itself, not more than 2. So if any number from 2 to array of I minus 1 divides array of I completely, that means this is a prime. Now quickly look at the array of I values. This is what must have come into your head now. Things seem much easier because life has been made easy. In the second problem, Leetcode gave you nums of I to be 100. That means specifically for this problem, even a brute solution would have worked. You could have said, let me keep array of I and run an iteration on array of I, running an iteration from actually 2 to array of I minus 1, and that will still work. Why? Because running this inner iteration, which I just told you, this inner iteration would have taken you a complexity of order array of I itself. Is that the case? And now if n is given to you in an order of 10 to the power 5, or to be exactly 3 into 10 power 5, and every number is a maximum value of 100, then what do you think is your time complexity to calculate this left part, this leftmost index? It is definitely 3 into 10 to the power 5 into 100, which is actually 3 into 10 to the power 7, and this is not going to give you a TLE. Yes, because in 1 second, you can have a maximum of 10 to the power 8 iterations. Definitely, there are better checks to calculate your prime. To be very optimum, maybe you could have calculated a sieve, or you could have done this in square root time to actually calculate the number of factors. Every other optimum approach was still there. But do you think you need to go there? Right? What happens in questions is, let's say for the sake of purpose, you could have come up with the most optimum solution. But during the contest, do you think if you can go ahead with the brute solution, you will think in such a direction, right? It's basic instinct, right? I look at the constraints, I see, all right, this solution can work. And if that solution is within my boundaries, I can make that out, right? So I know that a solution like this is definitely going to work, right? Again, optimally, if I wanted to optimize this, I could have argued that either I can find this factor check in a better complexity, and like just better complexity than this would be finding this is an O of square root of array of I, right? That is where you actually run an iteration in square root factors, and then you figure out that is it a factor or not. So that's also a case. In square root of 100 now, you would have decreased your complexity to not exactly 3 into 10 power 5, but actually 3 into 10 power 5 into 100. 10, not 100 exactly, right? So that would have given you a much lower time complexity. All right. Moreover, you could have next argued, what if I would have calculated some sort of a sieve function, right? By that sieve function, I would have marked all the prime numbers that come from 0 to 100. Then this would have been a constant time complexity, right? So I would have achieved a time complexity of 3 into 10 power 5 now, because I would have required constant time complexity to actually report whether array of I is prime or not. So all these conditions, all these checks definitely work. You applied a sieve, good to go. You applied a square root function, good to go. And even if you applied a brute approach, good to go. Because for all these three cases, your time complexity is coming within the boundary of 10 to the power 8. And I have submitted this solution. This definitely works. So it will definitely work for you. So I have discussed three solutions for you right now. Basic, simple optimizations in three parts. But my argument still rises is the brute solution works. And this becomes a mental note for you to always keep in mind what constraints are you looking at in Leetcode problems. All right. So if you have made a sieve function, definitely good to go. A square root function, more than good to go. And even an array of I, definitely good to go, because it barely, if you can say barely, but not exactly barely, but it definitely in a crisp manner passes your cases of not exceeding the TLE approach. All right, so this, I can now show you the code part for this, right? Basic stuff to understand. I'll take an L pointer that is -1 initially. That is the leftmost index I save. Now I'll run a J iterator in nums of size, J++, and then I'll keep a very simple check if nums of J is equal to 1. That means I need to continue because I know 1 is not a prime. Now I'll keep a flag variable that is 1, and then I'll simply run an iteration from 2 to nums of J minus 1. And then I'll argue, is nums of J, actually this can be equal to, right? This should be equal to. I'll argue that is nums of J modulo I equal to 0. If that is the case, then that means I divides nums of J completely. So I'll definitely make flag to be 0 and I'll break. And if that is not the case, if never flag turns 0, that means this current nums of J is definitely a prime, because you know that no other number from 2 to nums j minus 1 divided it. It means it only had two factors, 1 and the number itself. So if flag is still 1, I'll make L to be j and I'll break. And then I'm going to do the similar approach with a backward manner with taking r as -1. That is the rightmost pointer. Same approach, just the loop starts from nums.size minus 1 to 0 and in a negative order. Same approach inside, same code copy pasted, and now if you see L is -1, that means no prime was there, so you can return 0. And if there was exactly a prime that existed, you can return actually r minus L. That would be the maximum distance between the indices of these two primes you just found. Alright, so if you actually run this iteration on, let's say, the first case now, you will stop L at this position, that is I equals to 1, and you will stop R at this position, that is I equals to 4. And you will write R minus L, that is 4 minus 1 to be your answer, that would be 3. So this definitely works. It's a very basic problem. You can see you have a lot of summations to this. So I don't think it should be much of a concern that this should confuse you anymore. Alright, simple prime checks is what we were trying to find. What do you think is the time complexity? I would have forgotten to discuss this part, although I have discussed it right over here, but in a more formal manner, I can actually give this thing to you over here. What do you think is the time complexity? As I discussed, it's definitely n into, you can say maximum you are going is 100. So I can keep this as array of I, right? That would be a good optimization, good general term to keep, in which I can write that now in a maximum order, this is actually 3 into 10 power 5, which is n, into 100, which is maximum array of I, which is in order of 10 power 7, which is below 10 power 8. So definitely not a TLE. Alright, now what about space? Am I using any other data structure to store or report my answer correctly? No, I'm only doing two variables L and R. That means space is constant. Alright, it's good to go. Now we can actually look at the third problem and see how can we solve that out. Alright, so this is the third problem now, and I should say this is a pretty good problem. Alright, so this actually clears up a lot of concepts, and this is something new you guys will be learning today. So what is this problem actually telling you? You are given an integer array coins representing coins of different denominations and an integer k. Now you have an infinite number of coins of each denomination. However, you are not allowed to combine coins of different denominations. Alright, return the kth smallest amount that can be made using these coins. So you are definitely working with a single coin at a single point of time. So it's written you are not allowed to combine different coins. That means in this case, let's say the coins were 3, 6, 9. Then you cannot use to make a denomination with 3 and 9. You are only using this coin 1 to make different denominations as much as you can. And you have infinite amount of 3. So they have very clearly said that coin 3 will give you the coin denomination values as either you take only one coin 3. So that will give you a denomination 3. You take 2 coins of coin 3, you will get 6. 3 coins, 9, 4 coins, 12, and then 15, so on, up till whatever limit you can go. Same goes for 6. So 6 basically produces its multiples, 6, 12, 18, 24. 9 produces its multiples, 9, 18, 20, 27, and 36. And then we combine all these denominations in an increasing format, considering removing all the duplicates possible. You will say that the denominations I can finally achieve are 3, 6, 9, 12, 15, so on. And out of these denominations, the third denomination, that is the third smallest denomination being k as 3 is 9. So you report your k answer as 9 over here. Alright, so I think problem is understood now. Right, base point, given some coins, you know that those coins individually, every coin will produce its multiples from 1 to whatever max limit you can go, basically infinity, right? And when you do this for all coins, and for all coins, when you actually do this, sort them out and keep them in an increasing manner for everything possible, you will realize that I need this kth smallest amount out of all these possible denominations I can form, and this is going to be my answer. So similarly for coins, let's say 5, 2, k was 7. So for 5, you would have produced the multiples 5, 10, 15, 20, so on. For 2, you would have produced multiples 2, 4, 6, 8, 10, so on. Is that right? But what do you think is going to be now if you keep them in an increasing manner? You can produce denominations 2, 4, 5, 6, 8, 10, 12, 7, 14, 15, so on. And out of this, the seventh denomination you can form is 12. So K output was 12 for this particular approach. Alright, so now understanding the question, a very basic brute approach will come to your mind. You would have argued that what can I do? If I know I can have a well boundary on what K is, that is what is the maximum amount I can go. And then for a very I should say good amount of coins, what I can do is simply in some sort of a set structure, I can keep on inserting the multiples of every coin. And then set is sorted. Because set is sorted, then maybe I can convert that to a vector or whatever you can say. And then maybe I can actually bring out the kth smallest amount in this case. But the problem with this brute approach is, let's say you actually figure out that you have somehow figured out all the good denominations, and somehow you have stored all of them in sort of a vector or a structure, whatever you can say. The problem is K is given in order of 10 to the power 9. So to store these denominations, this structure should have a limit of 10 to the power 9 in space. Otherwise, you will never be able to do that. So if you think this approach is right, no, because then you don't have this much space, right? Can you form a vector or a set, or can you store actually 10 to the power 9, I should say, like in a single vector? Can a single vector be defined of this type or of this order? No, it cannot be. So this is not good to go, right? This is not good to go. I cannot store denominations. That is definitely my case. Now, if I cannot store denominations, that means without storing, I need to come up with an approach to actually check, right? Intuition becomes is, if I cannot store, without some storing, I need some approach which will give me quickly the denominations I could have formed. Is that right? But even if I want to make multiples of denominations, that is of coins of I, it would be very tedious for me to do. I need some better mathematics than this. Alright, so I'll try to shift my focus now. What will I try to shift my focus on? I'll say, alright, let me think in this direction. Let me say, there was some value x. Alright, there was some value x. And somehow, let's say somehow you have figured out your all possible increasing denominations, let's say d1, d2, d3, so on to obtain infinity. You were able to form whatever possible denominations you can. All of them are in an increasing order, with you. Now, let's say there is some number x with you. Tell me, for this number x, do you think you can give me the count of denominations which will come below the number equal to the number x? Let's say I ask you, let's say these were the denominations d4 also, d5 also, so on. Let's say maybe till d8 also you can say over here. Let's say I ask you, what are this count of denominations which were coming less than equal to x? If let's say there was some box, let's say there was some black box which would have given you, we are not concerned about how this black box functions. Let's say this checker function or this black box function was actually popping out this value c as a counter, which would have told you that this is the number of denominations in this particular array of all possible denominations in an increasing order which were less than equal to x. Then tell me one thing. If this black box function quickly pops up c to you, if c is actually greater than equal to k, or c is less than k, do you think you can now actually try to manipulate x's value so as to find your answer? What I'm arguing is, let's say for x you found out that c was the count of denominations which was coming out to be less than equal to x. Now let's say k was given 3 to you, and the count of denominations which actually popped up were, let's say 9 counts. All right, so let's say C was 9. So C is definitely greater than equal to K. Yes. So if C is definitely greater than equal to K, that means you are, what is your target? If K is 3, that means your target is to find this D3, right? That's clear. If your K is 3, your target is to find D3. And if you have just received a count to be greater than equal to K, that is 9 actually, that means you are standing at a denomination value which is not at D3 but actually on the right of D3, somewhere over here. That is why you are getting the count of denominations less than this value to be 9, less than equal to this value to be equal to 9. And you want that you land on this value, because if you land at this D3 denomination, you very well know that count of denominations less than D3 are 1, 2 and 3. That is exactly 3. So if you land at some other denomination for which you find your count to be equal to 9, or to be very honest, count to be equal to greater than equal to 9, greater than equal to 3, that means it clearly states you are standing at a denomination which is on the right side of D3. And if you are standing at a denomination to the right side of D3, let's say you are standing at D9. Let's say, just for example, you're standing at D9. Or to be very specific, you would be standing, let's say, at D9. If let's say you are standing at some D9, or I'll take general terms, not going in exact formats. Let's say you are standing at some DX. For this DX, you found that C was 9. Do you think your answer, even forget that currently you knew your answer was D3, which was standing on the left of side. Even if you did not know that D3 was on the left side, or D3 was actually in the left manner, so I should have gone to the left part, don't you think you can argue that all the denominations after dx will give me a C value greater than K again, greater than equal to K again? If up till dx the count of denominations less than equal to x is 9, then above this I'll definitely get more counts, right? Maybe 10, maybe 11, so on, maybe 12, and so on, so on, so on. So do you think going in the right side is helping me anymore? Do you think any denomination in the right side is a potential answer? No, it's not a potential answer anymore. That means all this area, all this space is actually a wasted space. Is that right? And I can actually now think in a direction that I need to search only in the space from D1 to, let's say, whatever is the denomination that comes before dx. Is that the argument? And let's say vice versa. Let's say you had landed on a denomination over here. Let's say you landed on, let's say, D2 denomination. Then for D2 denomination, you know, count would have been not 9, but rather 2. Because number of denominations less than equal to, let's say if x was actually some number, let's say some number that came before D3, let's say some number over here, let's say x, then count of denominations less than equal to x would have been only 2, that is D1 and D2. So you would have said that is the count 2, and since 2 is less than k, then do you think any other number less than equal to x, let's say all the other numbers over here, that is below x, will they give you a count of denomination equal to exactly 3? You need the count of denominations to be 3, right? No, and you are getting 2 currently. So any other number below x is going to give you denomination lower than 2, right? Or if 2 or lower than 2. So that means this space also is now a waste for you. And you can move on to search in this rest over space. Up till here, whatever idea I have discussed, I think you are now getting an intuition towards what I'm trying to point you at. I'm definitely trying to point you at a binary search concept. Is that right? Because I am actually figuring out to reduce search spaces as quickly as I can. And my argument is, for a binary search, the thing that I was trying to find was my answer, my most optimum answer x, for which I know that the count of denominations would have been exactly equal to k. The count of all possible denominations, if I would have placed them in a sorted manner, would have been exactly equal to k. So if I would have argued that there is a black box function or there is a checker function which would have given you the power to return this c value quickly, then don't you think this x in a space, in a search space, let's say I define a search space for this x, this search space of X is monotonic in nature. Yes, why monotonic? Because for, let's say this was the optimum place where you would have gotten your answer. So for this particular X, that is the optimum, or let's say this is optimum, so I'll name this as Y. Let's say this is the Y optimum answer which you actually needed to return. For this Y, you will receive the checkbox function to be true. Because you know for this Y, the number of denominations less than equal to Y actually turned out to be C greater than equal to K. Right? That was actually true. In your fx or the checker function, whatever you call this as. And for rest over values above Y, let's say this was another value y1, y plus 1, this was y plus 2, so on, so on, so on, till whatever limit you go as r, you can say, you know, all this are also going to give you true. Are they giving you true? Yes, because all the other denomination, all the other values greater than equal to y, that is your most optimum answer, will give you the count of denominations as greater than equal to k by this checkbox function. And every value below this, let's say this was y minus 1, y minus 2, so on, so on, so on, till the left limit, is going to return to you the checkbox value as c greater than less than k. That is actually simply false. Is that right? So that means I have two values only possible in this range. First of all, this range seems monotonic because I have false, 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 and then true, 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 true. And this is also predicate because I only am able to answer either with a false or with a true. So this checkbox function is actually returning me the possibility that if I have count of denominations greater than equal to k for a value x. This is what my function is actually doing. And because I have defined my function to be like this, it's either returning a true or it's returning a false. So this becomes predicate in nature, and the range I can see is definitely monotonic. So now do we get a hint that maybe binary search could have been used in this? Yes, right? Because now what is left for us is normal mistakes people commit is actually thinking first, how would you create checker functions? But before actually going in this part for creating checker functions, we need to make sure that what we are trying to find is actually something that is monotonic and predicate. So this is now a monotonic and a predicate nature. This has a monotonic and a predicate nature. The answer which I was trying to find, that is the kth smallest denomination value, not exactly denomination value actually. Yeah, right, exactly, denomination value only, right? So this denomination value is actually monotonic predicate in nature. So I know I can form a binary search solution in this. Now I can actually start putting all my focus to create this checker function. I can think in the direction, what can be the checker function? What all possible values of checker function can be there? What can be the most optimum method for me to create the checker function? All right. So this is where a new concept is going to come into picture, and this concept is going to be called as exclusion inclusion principle. All right, exclusion inclusion principle. We'll see what is this principle doing. All right, so I'll take up an example. I'll talk about this first coins possible. Coins are 3, 6 and 9. And let's say I was finding the answer for x equals to 9. Let's say I was finding the answer for x equals to 9. I want, give me the count of the possible denominations which would have fallen in the bracket of x equals to 9. So now, you know, let's say I first ask you, how many denominations do you think are going to be contributed by coin 1 for a value less than equal to x? You will say coin 1 has the value 3. So it is going to give me multiples of 3, that is 3, 6, 9, so on, so on, so on. That means if I divide this current x by 3, this is going to give me the count of coins or denominations, count of denominations which this individual coin 1 could have formed. Is that right? Less than equal to x. And this is pretty simple to understand. Yes, definitely the count is going to be 3. It's actually the denominations 3, 6 and 9. All of these three denominations can be formed by coin 1 and they are definitely lower than less than equal to 9. Now what about 6? Same case, x by 6. If I do that, that means 9 by 6. That is by integer division, you can say this is going to be 1. So the number of denomination 6 can individually form is actually a single denomination, that is 6. And then what about 9? You can say similar thing. If I do x by 9, this becomes out to be 1 again, because that is the single denomination this coin 3 can form, that is the denomination 9. So now up till here, if you add everything up, you will say that the number of denominations I have which could have been contributed are 5. But do you think they are 5 actually? No, right? Because there is some overlapping. What is the overlapping? You can see 6 is coming 2 times. 9 is also coming 2 times. How do you remove this overlapping? I wish to show you this by Venn diagram. Alright, because this is something many of you have studied in basic mathematics, and then you will realize that this is what I was trying to format. So what I've argued is this set structure which I've created, 3, 6, 9. I'll make this set structure to be called as a circle. This is a circle containing 3, 6 and 9. Then I know there is another circle which is actually the x by, which is actually giving me the possibility of the coin to formation denomination for this value x. This is another circle containing only the denomination 6. But because this denomination is overlapping with this first circle, I would cross it out with a denominator. I would make the circle to intersect with this denomination, correct? And I can actually now remove this 6 from here, and I'll argue 6 is coming in this. So this is for, if this is for coin 1, this is for coin 1, then this is for coin 2. Now what about coin 3? For coin 3, I'll say coin 3 has another intersection, and this intersection is looking somewhat like this, where I should have kept 9 over here, but this 9 is not at all anymore in this. This 9 actually comes in this case. This 9 actually falls over here in the intersection of this coin 1 set and this coin 3 set. So that means the net intersection now, the area of net intersection now is actually only 3. Or to be very specific, if you now represent this in Venn diagram format, in Venn diagram format, we have very clearly studied that in Venn diagram, if I want to calculate the union of these 3 areas, that is calculate the union of C1, C2, C3, isn't it written as the count of whatever would have fallen in C1 plus count of whatever would have fallen in C2 plus whatever would have fallen in C3 minus count in C1 union C2 minus count of C1 union C3 minus count of C2 union C3, and then if you remove this, like let's say I'll mark this with red, first you added up this area, then you added up this area, then you added up this area. Now, because you have added up this area, you know you would have added up this area twice. So you subtracted this once, you subtracted this area again once, and then you subtracted this area again once. So in that case, what you would have done is you would have also subtracted this area which you need to again add. So you will in front of this again write plus n of C1 union C2 union C3. Do you understand this? This is the case when I was talking about 3 possible coin values. And if now I have done this, I can actually calculate what is the correct answer for the exact number of denominations that would have fallen less than equal to this x value. Do you think that? And why have I named this exclusion inclusion principle? Because this concept which I was just talking about, if you extend this out to more, or to be a very general case, if you extend this out to be n coins, it is actually, the formula actually turns out as simply writing, if I want the union of, let's say, n of union of C1 union C2 so on till Cn, if I name this out, this actually forms as n of C1 plus n of C2 plus so on, you do this till n of Cn. This is done once. then minus, you negate the common two terms together. So you union C1, union C2, then plus you should say C1 union C3, then so on. You try to figure out all the two pair possibilities. Then now you add on all the 3 pair possibilities. So this is C1 union C2 union C3 and so on. Let's say you formed a possibility of, let's say C1, then maybe C5, maybe somewhere, like let's say just example, then maybe Cn, right? All the three possibilities. Then you again negate all the 4 possibilities. So C1 union C2 union C3 union C4. All right. So on. Then you add on the 5 possibilities, you subtract the 6 possibilities, and you keep on doing this till you reach the final possibilities of having everything covered. That is the last term to be union of all the values. That is C1 union C2 union to all till Cn. So this is n of C1 union C2 union so on union Cn. So this is actually called the exclusion inclusion principle. All right, and this is what we are trying to figure out. That is why this problem is pretty unique. This problem is pretty unique, and this is why you can see actually this has a very low count of submissions in right. If I actually yeah, definitely 700 submissions only. So normally problems like this, you can see this is difficulty rated hard, and problems like this actually have a very low count of submissions in that case. Also, this is what is happening in my case. All right, this is what is happening. That means if I want to calculate the common, the net total count of factors, I will have to use this exclusion inclusion principle. First, I would have calculated for individually every coin. Then I would have argued that I will calculate for two pairs of coins, then three pairs of coins, all three possible pairs of coins, then four pair, then five pair, and so on till it is possible. And every time I do that, I'll do this plus minus approach, because that is the inclusion exclusion output of the net union. And I have proved that by this extension in a showcase example of Venn diagram for 3 pair. All right. Now the next question rises is, all right, you have argued I want to deduce n of, let's say, C1 union C2. Or let's say in this case, the coin value 1 was 3, coin value 2 was 6. Then I would have argued remove whatever is the common part over here. In this common part, the value is 6. How do you actually get 6? Or how do you not exactly get 6? How do you exactly get the count as 1? Because you know there is only one number that is intersecting in the, I should say, with a coin 1 and coin 2 factor. It's basic sense that it means if I take LCM of 3, 6, it gives me, definitely it gives me 9, this should give me 9. And LCM of 3, 6, if I subtract LCM of 3, 6 from, I subtract the division of x upon LCM of 3, 6 now, that would mean I have subtracted 1 from this. That is, if x was 9, then LCM of 3, 6 was also 9. That means 9 by 9, that is actually equal to 1. And what is exactly meaning? What do I mean to say when I say you have removed this value 1 from here? That means that there was one common factor that was coming in the denominations, possible denominations from 3 set and 6 set. That was this factor. Yes, and you found out this factor by taking the LCM, because LCM of 3 and 6 turned out to be 9, and you deduce that this is the common part. I can remove this out. So if I can remove this out, I know that this gives me the power to exclude this 6 now. Now I'll do the similar approach for the next 2 pairs. I calculated this for 3, 6. I'll do this for 3, 9. What do you think is going to be the LCM of 3 and 9? LCM of 3 and 9 is definitely 9 again. So if I divide x by 9 again, that is x by LCM of 3, 9, then this gives me 9 by 9, this gives me 1. So again, you will remove 1 from the total answer up till here. So you will have 5 minus 1 again. Why this 1 again? Because this 9 was actually coming twice. This 9 and this 9 in the common denominations of 3 and 9 were coming again. So you removed this 9 and 9 again. And then you come up with the final part, that is, you have reduced all the
two pairs. So this was from two pairs, this was coming from two pairs, this was coming from only single pairs. Now you need to add on whatever comes from three pairs. So if you take the LCM of all these three numbers now, that is 3, 6 and 9. What do you think is the LCM now? The LCM for 3, 6 and 9 will be, I think, you have 3, 3, 9, this will be 18, right? And if you now divide 9 by 18, you will get by integer denomination division, you will get 0, which makes sense because now you know there is no other common factor which you had removed previously, which you now need to add. So you add on 0 into this, which gives you 3. 5 minus 1 is 3. And now you clearly know that yes, for x equals to 9, I had exactly 3 denominations which were falling in the increasing part of all the possible denominations. Alright, so this is where we have finally understood the problem. Started off with first understanding that the thing we are trying to find is a monotonic predicate, then actually coming up with its checker function. To come up with a checker function, realizing that I am, by Venn diagram, I can actually see that what I'm essentially trying to do is calculate the count of denominations which actually divide, which actually come before less than equal to 9, which could have been a possible multiple. So to do that, first take up all the numbers from individual coins, then negate 2 pairs, then add on 3 pairs, negate 4 pairs, add on 5 pairs, so on, because this is what would have been the case by exclusion-inclusion principle. Alright, you can actually search upon net and read about this much more and you will get a better picture. But I think by Venn diagram, I have clearly showed you that for a 3 part of for a case of 3 coins, exclusion-inclusion principle works like this, right? You take up, because your target was to calculate the union of everything, right? Your target was to calculate the union of this area. To do that, this is how you would have done. You would have calculated the sum of this area, then this area, then this area. Then if I change my pen, you would have decreased the area this, and then you would have again increased on the area this green area. Alright, so this is now the answer to the question. So what finally boils down the approach to? Now what can I do is, I can pre-hand calculate what is going to be the possible LCM's value, or individually this NC1, NC2 or NC1 union C2, all this individual values in some sort of a data structure. And then what I can do is, when I calculate some X value by binary search, for this X value, I can run a iteration on this data structure and then add or decrease however I wish to, like whatever is the number of value I should have actually done with. Alright, so now why is this approach coming to my mind to do actually pre-calculate this? Because you can see that coin's length is pretty small. It's in 15 order, and every number coin is also very small. It's basically 25. So if that's the case, don't you think I can brute out this? I can brute this out. That is, you have some coins. You have coin 1, you have coin 2, you have coin 3, you have coin 4, coin 5. And what do you wish to do is, you wish to calculate the LCM of the every possible subset in this 5 coins. If let's say there were 5 coins, so you would have argued, or let's say I'll actually decrease this out. Let's say you only had 3 coins, then your argument would have been, I wish to store the LCM of individually a single number, let's say C1, then C2, then C3, then I wish to store the LCM of C1, C2, LCM of C1, C3, then LCM of C1, C2, C3. So this is for size 1, this is for all possible sizes of 2, and this is for all possible sizes of 3. So now you know that the maximum coins that are given to you are 15. So if you form a sort of a recursive helper function where you actually, what is the general case of actually doing this with subset format? In subset, how do we do this? We do an approach of take not take condition, right? Take or not take condition. Either you take C1, not take C1, take C2, not take C2, take C3, not take C2. If you do this approach, what do you think your recursive call stack is going to have your time complexity as? You have maximum 15 coin values. So that means you will either take first coin, not take first coin, take first coin, not take first coin, so on, till 15 times. So don't you think you will have a maximum recursive call stack of 2 to the power 15? Yes. 2 to the power 2 to the power 15. And this number, right, this number actually in, let's say, I think I actually had searched this up only. 2 to the power 15 is 32768, which is actually a, simply you can say 10 to the power 4 order, 32768. So don't you think a simple recursive call stack will help you calculate the LCMs of all possible subsets possible? And then when this is done, what you can do is, for an x value now, add upon x by whatever count falls as whatever number, whatever this value is, right? Whatever this value comes out to be, whatever this value is C2, whatever this value is C3, that is, you add upon that, then you minus LCM of C1, C2, x by LCM of C1, C2, x by LCM of C1, C3, and then you add x by LCM of C1, C2, C3, and this pattern can be followed whatever number of denominations you have. Alright, so I hope I have given justice to the problem, right? Again, this is a very typical and a very ad hoc based problem, and this is a unique problem set. Alright, so if we can look at the code part now, and you will quickly understand what am I doing. So naturally what I've created is, first I'll show you how am I making my helper function work. So I have created a DP. Alright, you can call this a DP, you can call it whatever you want. My head was to run in a DP format. So I'll create this DP. Size is it's a 2D DP definitely, where I will say that every row, the row is going to represent the size of the current subset, and in the column I have saved all the possible LCM values. So I'll say DP's maximum size is 16 in the row function, because I know maximum coins are 15. Then what I'll do is I'll call the helper function by passing this coins vector. The first index starts with 0, then the LCM that starts with 1, and then the current count of coins I have chosen as 0. Initially I have chosen no number of coins, so it is 0. Now what will I do? If index turns out to be greater than equal to coins size, that means I need to stop. So whatever is the current count of coins I have selected in my subset, I will push back the current LCM in this DP of coin count, and then I'll return. Then if this is not the case, I am going to move on to the next part, where I will first give the not take call. That is, I will keep coins as it is, LCM as it is, count as it is, and I will only increment my index. And then this becomes my take call. How do I calculate the take call? If LCM is currently 1, that means this current number coins of index is the number I want to start with. So I'll say jump definitely to the next index. The LCM now starts with coins of index, and in a long format in 1LL. And then I can say count of the current coins which I've selected in the subset becomes +1. So this is the take first possible coin when LCM was 1. And if this is not the case, that means I need definitely coins, jump to the next index, definitely count gets added, because this is to a take condition. But what is the new LCM now? LCM is whatever was the previous LCM into coins value upon their GCD. Why? Because I know a very small mathematical trick where I know that calculation of two numbers A and B, if I want to calculate the LCM of two numbers A and B, it's actually equal to LCM of A comma B into GCD of A comma B is actually equal to A into B. So if I want to calculate LCM of A comma B, I can just bring this down. Alright, so because I have a very good HTL function in C++ with me, that is __ GCD, for me to calculate in a good time complexity what is going to be the GCD of the given, I should say function, given two values, that means I know I can pass this on to calculate the GCD now. Alright, and then if I finally return, in this DP, I would have for every row value, I would have saved whatever are the possible LCM values or not. And then what do I start off with? Now I'll start off with my binary search. I'll declare my left starts with 1 naturally, because that is the lowest denomination you could have formed actually, sorry. What do you think is the highest denomination you can go? Right, not specifically by mathematics, you can definitely calculate this, but on a very safe side, you know that since every coin value is 25, let's say the possible answer was, let's say every coin value is only 1, then the maximum denomination size you can calculate is 2 into 10^9, right? So a good limit would be to take a very big number. So I have taken this number as 10^12. Now I have a number answer and I binary search. Left is less than equal to right, calculate the mid, calculate the C value, and a flag variable, that is f equals to 1. Why this flag variable? This flag variable is actually the sign variable which is helping me shift. So initially I know I am trying to add on then minus, then add, then minus. So what I'll do is I'll run my iteration from 1 to less than equal to 15 in the DP. And if this current size of DP of I is greater than 0, that means there are some LCM values for me to reduce. So I'll iterate in this DP of I with the iterator with the value IT. Now if f is positive, that means I am first increasing the count. So I'll increase count by mid by IT. That is, mid means x, so x by C1, x by C2, x by C3, so on. And if f is 0, that means I'll decrease because now I need to exclude. First I included, then I excluded. So I need to exclude mid by IT. And then when I end this iteration, I will make my f flag to turn as different value now. So if f was 1, now f becomes 0 because next time I want it to be, I want to exclude, right? So I want my f to become 0, then it will become 1, then 0, then 1 and vice versa. Now if I finally come out of this loop, if C turns out to be greater than equal to K, I can very well say that answer is equal to mid, and I will decrease right to be mid minus 1. Why? Because in my predicate monotonic function, I just saw that if I was standing at some value over here, I need this first true value, right? So if I want this first true value, if I stand, let's say over here, then I know I want to decrease my right space to this place, or if I stand over here and I get a false, I want to increase my left space to over here. So I'll say if C is greater than equal to K, answer becomes mid, else and right becomes mid minus 1, else left becomes mid plus 1. Alright, and if you actually return your answer, this is going to give you the right piece of code, and I think this is definitely working also. So if I submit this out for you guys, yeah, this is accepted code. So like now what do you think is going to be the time complexity of this? Alright, like this helper function which I'm calculating, I told you the time complexity of this is 2 power 15, right? To be in specific order, you can say 2 power 15 is a good space, right? Or in general terms 2 power n. And the binary search I'm doing is a simple binary search which you can say runs in, if I would have taken this as 2 into 10 power 9 also, this would have worked, right? Or I can actually take this as k also, that would have also worked. So I can say binary search is in a rough format, I should say, rough order of k. Sorry, log of k, right? So binary search. So this is a log of k format. And inside this iteration which you are doing, which this inner loop which you are actually working, this is 15 iterations max. And for every 15 iteration, you will have at max, like number of pairs will be very small, right? So like if you're talking about 2 pairs, then you will have exactly like 15 C2 pairs, that would be very small, like I think 15 to C2 will be 15 into 7. All right, that would be approximately I think 70 and then like 100 pairs almost, right? So like at max, the inner loop, this inner DP loop that is actually running is at max 100 pairs, or you can say at max n, right? At max actually n to be like for one denomination it will have 25, then for 2 it will have actually 100, correct? And then for one denomination it will have actually 15, right? So 15, and then for taking 2 out of those as a pair, so that is 15C2. That can be 15C2, actually not 15C2, actually 15P2, right? So for 15P2 that would mean less pairs actually, right? Not more. So I think we'll have yeah, so this actually inner loop is actually like kind of, you can say, for single runs in 15, then much lower than this, right? Then much lower than this, and so on, so on, so on, right? I think that is basic mathematics. You can calculate that on your own. That's not going to be a big deal, right? The point being is this if loop is not running in a very high iteration. This is maximum 15 into some factor 15, which is also at max. In my case, I can see this is 15 going. That is almost in 200, in 100, or you can say 10 power 2 factor. All right, that is the inclusion factor which we are doing right now. So what do you think is the time complexity now, right? This solve function which you have, this helper function which you have called, is actually an external function. So you can see that time complexity over here starts with adding this. So this is 2 power n plus this is running in log of k. Log of k inside which the checker function is running in maximum of 10 power 2 iterations, right? Like 10 power 2. Rough, I'm doing a very rough estimation, but you realize that this is not very huge, right? Even like even if this goes 1000, it's fine, because I know log k is not a very big term. Log k is not going to be a very, very big term, because for 10 power, even for 10 power 12 order, log k is maximum 40 to 50 iterations. I think that is also, I'm being lenient. So you get a very basic time complexity where you can say that this is in an order of, like, let's say I had just showed you that 2 power n, for n being in 15 order. This is actually in 10 power 4 order, plus then inner this is, let's say this is actually maybe in a lenient case, let's say this is 100 iterations, and this is, let's say, maybe 1000 iterations. Even that, then the in this iterations is 10 power 5. Not exactly 10.5, it would be definitely lower than this, but let's argue, even if it's 10 power 5, not definitely above that, even then you get an order which is still working, because this order is still in 10 power 4 to 10 power 5 order, and this is well within my boundaries, because in 1 second I know I could have done a order of 10 power 8, so this is good to go. And as I just showed you, when I submitted the code also, it got accepted. That means yes, the time complexity was within my boundaries, or it would have given me a TLE. Alright, so a rough approximation of the time complexity, right? Exact can be calculated, exact iteration, exact value can be calculated by you, right? Basic mathematics, but it's not going to be a big deal, right? It's the base idea is to understand that approximately it fits within my boundaries. And what about space? What about space? Space is definitely 2 power n, right? Because I have the dp that is getting calculated, and I know for this dp like not exactly 2 power n, right? Not exactly 2 power n, sorry. dp you can say is the maximum row size is 15, right? So I know space for the dp is 15 into what is the number of, I should say, save I am actually doing for the number of iterations that is actually happening. So number of savings that I'm doing per column, right? It's not going to be above like 100, 200 per column, I should say, LCM values, right? So I know space is also within my boundaries. Like space, I can give a rough approximation, maybe in 10 power 3 or 10 power 4 order can be a good approximation. That's I'm being lenient, right? It's not going to be in that order definitely, but I should say well within my boundaries. Alright, so rough approximations for everything, right? But idea should be clear, right? Idea should be clear. Main logic over here is actually for the time and space only, right? And main idea is to grasp binary search, right? This is a very good problem in binary search. I should actually categorize if I should put that. Moreover, there's a very new concept called exclusion inclusion principle that gets involved in this. All right. So this is what is all about the third problem. Now what we can do is actually jump onto the fourth problem and see how can we implement it out. So this is the fourth problem, right? This was again a hard problem, and this is a very classic problem if you figure out what the constraints are and if you realize what are we doing. So we'll try to bring up some intuitions and ideas in our head and see what can we do in this out. All right, so problem is basic. Problem is pretty basic. Problem is written. You are given two arrays nums and array ands values of length n and m respectively, and the value of an array is equal to the last element of an array. So what they have defined this as that whatever value of an array you take, it's the last value. Last element of that array is called the value. Now your target is to divide nums into m disjoint continuous subarrays such that the ith subarray from L to Ri, the bitwise AND of this subarray is equal to this AND's value. And in other words, you can say nums Li and nums Li plus 1 and so on, nums Ri is equal to AND's I value. And you are going to do this by making sure that you find the minimum possible sum. So when you do this, when you actually divide the nums array into m disjoint continuous subarrays, you will argue that when I do this, my target would be to achieve the minimum possible sum of the values of the m subarrays. Is that right? So my target would be that when I do this, I will be taking the minimum possible sum of the values. Values meaning last element of the array. And if I see it is not possible to divide num into m subarrays satisfying these above conditions, then I will print a -1. So the problem is pretty typical, right? It is well given to you what you need to create as an AND value. And it is well given to you how many subarrays you need to create. You need to create m values. So let's say if you talk about the first case, it is given that you create, if you take this one segment 1 to 4, it will have a value as 4 and this AND is 0 and it matches with the 0. So Good to go. This segment gets mapped to this segment. Next time, this segment gets mapped to this segment, and is 3, and the value is 3. This value 3 and 3 matches next segment, and this value 2 and also 2 matches, and you have 4 segments of 0, 3, 3, 2 ands, and the value becomes 4 plus 3 plus 3 plus 2, and that is 12. And their argument is this is the lowest I can go. Alright, and similar is the case with the example 2. So now the problem actually is to figure out what sort of a complexity should I achieve in this case. And this is where things are going to look interesting if I look at the constraints part. Nums is pretty huge, right? So nums array is 10 power 4. But if you look at the AND values length, it is very small, right? It is small, and it is actually small in 10. That means the maximum M subarrays you need to divide are 10. You cannot go beyond dividing 10 subarrays, 10 continuous segments of subarrays. Alright, so this is first observation. Second observation is, I know that whenever I do AND, like let's say I do A and B, let's say this value turns out as C. If I do AND of C with another value, let's say D, and this other value turns out as, let's say, E, then I know for sure E is less than equal to C. Why? Because ANDing, bitwise AND, always reduces the values. Bitwise AND always reduces values. Alright, meaning if I keep on taking bitwise AND more and more times, the more higher possibility will be I'll be turning off bits. Because in bitwise AND what happens is, if any one of the bit is 0, then the bit turns off. Because you know 0 0 also gives you 0, 0 1 also gives you 0, 1 0 also gives you 0. Only and only if both bits are turned on, you get a 1. So if you keep on taking AND so on multiple times, there is a high probability that you only reduce the bit. You never turn on a previous bit. So if the previous bit was actually 0, it remains a 0. And if the previous bit was actually 1, only and only if there is a 1, it remains a 1, else it turns 0. So there's a high possibility that you reduce the bits and never increase them. So the moment you keep on taking more and more times between AND, it reduces. This is second observation. Now the third observation is, which is actually the most crucial and essential part of this question, alright? This is some observation which if you would have made on your own, and like if this observation comes to your mind, it mostly doesn't come to everyone's mind. Alright, so this is a very important and a very fun observation for this question to pass. Alright, what will happen is, like as we discussed, AND is always decreasing. Alright, so like maybe you will argue that since nums of I is in 10 power 5 order, that would mean that if I calculate the all possible AND values, like if I maintain a state of AND values, and whenever I say that I'm taking the AND, I take out the AND with a value, you might argue that it is possible for me to visit all the states of all AND values. Because like let's say since nums of I is belonging to the range 1 to 10 power 5, then you can argue that it would be possible for me that all AND values are created. But ideally that is not the case. Alright, ideally what happens is, the argument at max, like there are not going to be, like it's not possible for you to visit all the AND value states in this case. Meaning what will happen is, my idea was going towards a DP solution, right? What I could have done is maintain 3 states. Let's say this is state 1, state 2, and state 3. So what would have been state 1? State 1 would have been the I iterator, correct? I iterator, which is actually running in 0 to n-1. That is running on the first array. Then I can keep a state 2, that is the J iterator, which is actually running in 0 to m-1 maximum. And then this third state would have been the current AND value which I have. So what would I have done essentially is, let's say this AND value, the possible states of AND value was very low, then what would have happened is, in your DP, you would be running a take, not take sort of a DP, where your solution would have been in such a direction. You would have said, I will either take the ith number or I will not take the ith number. When I take the ith number, I am going to AND that current AND value with that number and move on. If I don't take that number, then I'll not move on. And when I do that, I will also keep checking that current AND has the current AND become equal to the current AND values, possible AND values that was given to me for the jth index, where j is starting from 0. If that is the case, then I could have incremented j also. So likewise, just to think of like we will go into the depth in the code part to what states and how will I actually maintain the helper functions. But if you just out of the basic mind calculate the time complexity, you will argue that alright, state 1 would have a time complexity of 10 power 5 because I iterator, sorry, not 10 power 5, 10 power 4, correct? 10 power 4, maximum 10 power 4 into state 2 is running in maximum 10 because this is the j iterator that is running in M. And then you will argue that state 3 is actually the AND of all possible values. And since AND of all possible values is like all the AND values are exceeding till 10 power 5 limit, that means you can say state 3 can have all possible states or could have had all possible states in 10 power 5 order again. So this would have given you a TLE. This solution would have given you a TLE even if you would have memoized this in a DP format. Why? Because this solution directly looks to me as a 10 power 10 solution and this is definitely a TLE. But the argument is that is not the case. If you actually run this solution, you will actually see that it gets accepted. Now, mathematically, to be very detailed, why does it get accepted? That is something that is like it's a very complex mathematics to show and actually prove out. But on a very, I should say, boiler scale, you can imagine is this state 3. If it's getting accepted, that means definitely state 1 was in 10 power 4 order. State 2 is definitely in 10 order. But if state 3 is getting accepted, that means state 3 was not in 10 power 5 order. It was definitely something below than this order. That means it clearly means that when you take the AND of the possible values till some ith index, when you do a take not take condition, the possible values of AND are never the possible value, like the possible, all possible values of AND are never in a order of 10 power 5. They're definitely in a lower order. And to be very specific, you can actually find this in a sort of an editorial format in the problem itself, where people have argued that what will happen is, if you create a simple not take condition, like let's say I'll zoom this out, what is happening is consider n equals to 20. If the person has written, if the math is correct, the probability that the AND value results in 0 is 1 minus 1 upon 2 power 20 whole power 20, which is approximately 0.99999999 something, which means increasing n tends to increase this probability towards 1. Now, it is clearly written by this formula. If we examine each bit independently, there is only one scenario where the bit is preserved. That is when all the numbers that have that bit set to 1. Now, with 20 numbers, each bit has a probability 1 by 2 of being 0. Hence, there are 1 upon 2 power n value distributions where only one preserves the bit and the other results in 0 and value for that bit. Now, considering approximately 20 bits, why 20 bits? Because for a number of 10 power 5 order, you can keep approximately 20 bits as a good number, right? Representing 10 power 5 integer in bit format will give you approximately 20 bits. To be very specific, it gives you, I think, 17 to 18 bits, but on a safe side, you can keep this as 20 bits. So the argument would be that to preserve the number, to keep different values of AND, you would require a 1. And we just deduce that ANDing more and more ANDs gives you lower and lower values, because the probability that you reduce the bit or turn of that bit is very high. Reason being that if any bit out of taking AND, let's say you're taking up AND till here, if any bit in all these numbers is 0, then you will get that bit turned off. That clearly means that you have, if let's say I'm taking 20 numbers, you have 1 upon 2 power 20 probability to turn off that number. And to turn on that number would be 1 minus 1 upon 2 power 20. Is that right? Now considering this is for 1 bit. Now considering for 20 bits, this get again multiplied by 20 to the power of 20. So this is a rough approximation you can deduce mathematically that this state 3, which is the AND of the values, this state there is very high chance that this state 3 does not has unique values in order of 10 power 5, but maximum this is going to have, I think, maybe 20 to 30 values. That is all. State 3 is going to have maximum 20 to 30 possible values. All right. Reason being that the state of turning of the bits is so high, probability of turning of the bits is so high that you will not get a lot of unique possible state 3 values. That is the AND of the current and AND value. So that means mathematically what can I do is I can try out that let me form this sort of a DP solution where I maintain a state 1, state 2 and the state 3 will be current and then if I can see if that passes out, right? And mathematically I can actually figure out that this should give me an AC. Because if that is the case, if now I calculate the time complexity, it would turn out as 10 power 4 into 10 into, I am arguing that around 20 to 30 numbers. So that means in order of 10 power 6, right? 10 power 4 into 10, that's 10 power 5 into 20 or 30 maybe, that means approximately 2 into 10 power 6 to 3 into 10 power 6, which is definitely within my boundaries, not going to give me a TLE at all. So this was the uniqueness in the problem, right? Again, this problem could have been solved with some other method, but again, you should be possible to all mathematics and all different approaches that are out there. All right, so I mean, I think a more complex approach to this would have been using segment trees, right? Editorial for that would also have been present in the states, but a solution that I had made in the contest was this, and I had deduced this by general guesswork and basic mathematics that state 3 is not going to have a lot of possible values. All right, and that is why I think this solution definitely works, and this is what the argument can be for all the other solutions that is actually working in this case, and many people have argued like this also, like this mathematics, many people have argued. So now what does the approach finally becomes? Let's forget about the fact that let's say this state 3 was going in 10 power 5 order. Let's say I give you for short a proof that this actually is in only 20 order. Then do you think now you can create a very basic DP solution of take not take condition? You can, right? If we can actually look directly into the code part, we'll understand what will be try to implement. So what I'll do is I'll maintain a DP, right? In this DP, I have 3 states, definitely. And in this, I'll have a first state and then I'll have a second state. So what I'll do is I know that because the third state is amortized, it is not in exactly 20 or 30. I don't know the exact count of what state 3 can be. So I'll take the state third to be in a map function. So what I'll do is DP will be created in a vector of unordered map of in, in type, right? Why unordered? Because I want the lowest time complexity possible to actually call a state. So unordered map gives me order of 1 complexity to do this. And then what I'll say is, I'll run this DP function in the main using this helper function for recursive call. What I'll say is I'll extract first the size of nums. Now I know first state is definitely the size of this array. So I know I'll declare my DP's first size to be n plus 2. And then the other side, I will declare my vector of unordered map, and the second state is going to be in, I will keep that as a, since this is m and m is in order of 10, so I'll keep this as a safe side 11 order. So I'll declare this to be an 11 order. And then the third state is something that is maintained in a map, so I won't be concerned about that. Now what will I do? I'll pass on the helper function. I'll pass on this nums array, the AND values array, the initial index for running in nums, that is 0, and the initial index that runs in AND values array, that is also 0. And then I'll pass on this third state, that is the current AND value which I have. Now the current AND value, I'll begin with a very big AND value that is all ones in nature. So that means what I'll do is I'll pass 1 left shift to 19 minus 1. Since this is going to give me a value that is like bitwise, what happens is, like if I say I'm shifting 1 left times to 19, that means I have a number that is 1 0 0 0 0 0 0 something till 19 times, and if I subtract 1 from this, actually I get a number that is 1 1 1 1 1 1 1 1 1. All right, approximately 18 bits in this, and this is a good approximation to keep 18 bits. Why? Because I know that the maximum number nums I is actually in 10 power 5 order, which has maximum 17 bits. All right, so it is good to go. Now, what will I say now? Now, if I have actually passed on this initial AND value in the helper function, if this current, that is the current index in I, if this current index in I, that is in the nums array, crosses the nums size, then what will I say? If that is the case, so my base condition becomes, if current size is greater than or equal to nums size, then if the AND current, that is the running iterator in the AND's values, also crosses the AND values dot size, that means I was for short able to make m continuous subarrays segments. So I'll return a 0. And if that is not the case, that means if I exhausted my nums array, but I was not able to exhaust all the AND values, that means I was not able to create continuous segments. So I will return 1e8. Why 1e8? Because I need the max, I need to minimize later on. So I'll return a very huge value. All right, so I can actually I could have actually kept that as int max also. That is still going to work. All right, int max also, that still works. Because I need the minimum later, right? So I'll declare this as to be max. Now else if let's say current did not cross num's size, but the AND current iterator that is was running in the second array crossed its length, then I will also return int max, because that would mean that I have not exhausted my initial array, but I have exhausted the possible AND values. So I'll return int max. So this becomes my base conditions in the DP. Now what do I do more? Now because this is a DP, I need to use the previous solutions if possible. So I'll say if the DP of current state and current state dot count the AND value, that is if the combination of state 1, state 2 with the state 3 is already present, that means I will return DP of current and AND, current and AND. Correct? Current and AND. And if that is not the case, then I will calculate. How do I calculate? I have declared two variables. First is became equal. Became equal means up till the ith index where I was wanting to cut off, the value became equal to the AND value. So it starts with int max, and now I check if the current AND with the num's current value ANDing both is equal to the AND's value of AND current iterator, then I know this is a place where I can break off. So become equal becomes actually equal to num's current. This is the last value that would have been at the current iterator to denote the sum, plus now I will call the helper function again and everything gets initialized back, right? Current becomes +1 because I will definitely jump one iterator again in the main array. Since I have utilized this AND value, I will jump the AND iterator also by 1. And what becomes the new AND value? The new AND value gets initialized back to 1 left shift to, I can say 19 actually, -1. Because now I know I am ANDing again, so now I need to reinitialize my AND value back. Because this is where I have a cutoff. This is the place I would have cut off. And now, if I want the other variable that is did not become equal, that would be equal to simply saying that I would have skipped this, I would have taken this value and simply jump this iterator. So I will say current +1 and then AND value with the nums of current. So not checking if this case, this becomes the other value. In this case, I would have not taken the sum because I know this is where I'm not breaking off. This is some place I don't need to break off. So I'm not going to add to the helper function nums of current. Now, whatever is the two states out of this, two calls out of this rather, become equal and did not become equal. Minimum of these two get saved in DP of current and the current A and D state. So I should actually return this int max to 1e8, right? Because what the problem would be that with int max, there would be a possibility that when you AND out with int max, you get a value that is greater than int max, and then you would not be able to save that value in the int data type, right? So this needs to be 1e8 to be specific, right? It should not be int max, although you get the concept, right? We need a very high value, so I've taken this to be 1e8, right? Which definitely fits my boundaries, and if you AND this out, you will still remain within the boundaries of int. Other case could have been, let's say you take int min, int max only, then you could have taken long type. So either way that works. But this should be in I1e8 or some value actually in that order for this to work in the int boundaries. So now if I actually run this out, expected would be a TLE. All right, expected would be a TLE. But if you see, if I submit this out, you will not get a TLE. You are going to get a right answer. All right. Yes, accepted. So that means somewhere or the other in the backend, conceptually something was happening in the complexity that was helping you get into the state of not crossing the limit of the DP. Is that right? And you can realize that since state 1 was definitely in 10 power 4 order, state 2 was definitely in 10 order, that means the state 3 which was expected to be in 10 power 5 order was not in 10 power 5 order, it was something very low. And the only possible explanation of that is if it was low, it should have been low enough to 20 to 30. And mathematically, I have given you a very small proof so as to see how is it coming. You can definitely Google this out and look more into this concept. But conceptually, this is what would have been happening in the background, and that is why the solution is getting accepted. All right, so all those you would have formed a solution like this. I hope you have understood why this is happening, and all those who were not able to deduce this, that this could have been an approach, here you go. All right, so I think now we can discuss the time complexity of this. So as I discussed, time complexity in order should be actually in, like, you can say this as O of n, right? O of n into m into, you can say this is 20 to 30 iterations, right? 20 to 30 iterations, and 20 to 30 iterations, to be very specific, can be actually written as simply log base 2 of, or writing log of actually 10 power 5 also, right? 10 power 5 also. That is also good iteration. Or to be very specific, log of maximum element in the array is also very good. A very good approximation, because you know that whatever is the, like, I took 20 iterations because I know 20 to 30, because I had argued that the number was 10 power 5. So you had 20 bits, but let's say you had lower number of bits. Let's say you only had 10 bits. Then do you think this complexity, this probability is now standing true? No, right? So lower the number of states. So don't you think that it is kind of dependent on what is the highest maximum element in the array? And the log of that means whatever is the maximum bit you can actually turn on in the number. So log of max element is a good way to go. So that means you can write this as actually O of 10 power 4 into 10 into, or to be 11, right? To be 11 into, you can say log of this, which is actually, I think for 10 power 5, log base 2 for 1e5, I think is, yeah, 16 iterations. So I can say 16 to 17 bits, right? So I can keep this as 16 to 17 bits, which approximately gives me a complexity of 10 power 6 order. Is that right? So 10 power 6 order is a good order to go. Now this is definitely within my boundaries and is not going to give me a TLE. And we just proved by basic probability also and submitting this out also that we saw that yes, this was definitely working. That means yes, the time complexity is within my boundaries. Now what about space? I'm using this DP, right? Definitely. Now space is definitely dependent on whatever I'm saving, right? So space automatically becomes equal to this. I don't need to think beyond that. Space is definitely going to look n into m into log of max element order only, because that is the number of states I would have maintained in the DP. All right, so this is time complexity and space complexity finally. I would definitely agree that this problem is a very typical problem, right? I think problem 3rd and problem 4 today were also kind of on the harder side and or the very ad hoc and a very typical problem side, but then again, something for you to learn every day. All right, so I think this is a good place we can stop. Thank you for watching the video. I hope you like it.